Welcome to the AI Prompt Forensics Lab. Today, we've got a pivotal piece of AI history on this lab, the Alpaca Prompt Template. Now, I know, it might just look like a bit of plain text, but trust me, this specific format, this was the catalyst that completely changed how we interact with large language models. So let's just dive right in. Back in early 2023, we were all wrestling with this one central engineering puzzle, right? We had these incredibly powerful models, amazing at predicting the next word, but they weren't really helpful assistants yet. Not really. So the big question was, how do you actually bridge that gap?
You see, these early base models like Meta's Llama, they were incredible predictors. You could give them the start of a sentence and they'd finish it just beautifully. But ask them to do something specific, the results were, let's just say, all over the place. It was basically autocomplete on an industrial scale, not a reliable tool you could use for actual tasks. And that's the core challenge we're going to dig into today.
And that brings us to our key artifact. Because, the solution wasn't just to build a bigger, more powerful model. Nope. It was about finding a smarter way to teach the models we already had. And that's where this case file comes in. The Alpaca format. It was a genuine watershed moment for open source AI. And just look at how fast this all happened. It's wild. In February 2023, the whole community gets its hands on Llama. Then, just 1 month later, boom, Stanford researchers drop Alpaca. This kicked off what a lot of people call the stable diffusion moment for language models. All of a sudden, high-performance fine-tuning wasn't something only the big tech giants could do. The gates were thrown open to basically everyone. So how accessible are we really talking here? Well, get this. The total cost to replicate what the Stanford team did was about $600. $600! This wasn't just a technical breakthrough. It was an economic one. It threw the doors wide open for academic labs and, heck, even individuals to get their hands dirty with cutting-edge AI research. So how on earth did they pull this off for so cheap? This is the really crucial part. They didn't have some massive, expensive, hand-labeled data set. No. Instead, they used this incredibly clever technique, often called self-instruct. They just prompted OpenAI's powerful Text DaVinci 003 to generate 52,000 examples of instructions and their corresponding responses. You see, the real innovation here wasn't just the model itself. It was the structured data they used to teach it. All right, time to get our hands dirty. Let's get this template on the forensics table and really dissect its components. We're going to reverse engineer this blueprint, piece by piece, to figure out exactly why it worked so well. Okay, at its heart, this template is really just a grammar for communication. Its main job? To solve what we call the boundary problem. It needed to make it crystal clear to the model, hey, this is the humans part, and okay, now it's your turn to start talking. And that right there, that's our first big insight. It's the structure that tames the complexity. First up, component 1, the instruction. It's clearly marked with hashtag instruction. It's the mandatory part, the task description. It's super direct, totally ambiguous, and it tells the model exactly what it needs to do. Next, we have component 2, the input. This one is optional, marked with hashtag input. This is where you feed the model the actual data for the task. So if your instruction is translate this into French, well, the input is the text you actually want translated. What's interesting is that the original Stanford dataset used this field about 40% of the time, which is what gave the model so much flexibility for both simple and more complex tasks. And finally, we get to what I think is the most critical part, the response marker, hashtag response. This is the trigger. This is the magic signal. It's basically the cue that tells the model, okay, stop listening, start generating, it's your turn. During fine-tuning, the model is taught over and over again to only start producing text after it sees this exact sequence. So, when you put it all together, the template really has 2 main flavors. You've got the full version with an input field for tasks that need extra data, and then you have the simpler version for when the instruction has everything it needs. This kind of flexibility was absolutely key to why it was adopted so widely. And this quote here just nails the concept. These simple, plain text markers, they're not just text. They act as what you might call cognitive anchors for the model. They create these clear, distinct roles, the user and the assistant, and teach the model how to switch between those personas. It was just an elegantly simple solution to that really tricky boundary problem. All right, let's move on to the pathology report. Look, no engineering solution is ever perfect, right? So we need to put this under the microscope and examine not just its strengths, but also its vulnerabilities, its inherent trade-offs.
And what's really fascinating here is the trade-off. On one hand, its strengths were groundbreaking. I mean, it was simple, it was accessible, it was super reliable for single-shot tasks. But on the other hand, it was definitely a product of its time. It just wasn't designed for multi-turn conversations, and it had some real vulnerabilities, like being open to prompt injection and having issues with syntax clashes.
Okay, and for any engineers out there who might actually work with this format, here's a heads up on some critical gotchas. First, that 300 hashtag delimiter, yeah, it can easily get confused with markdown headers, which can totally screw up your input. The format is also incredibly sensitive to tokenization. Like, a single missing space after the response marker can cause the whole thing to fail. And then there's a really common error, the double BOS token, which can completely break instruction following. The takeaway? With these older formats, precision is absolutely everything.
Okay, so now that we've dissected the original, let's look at its evolution. We're going to place our artifact here in its proper evolutionary lineage and see how these foundational ideas grew and were adapted for much more complex systems. And this chart, this lays out the whole progression beautifully. You start with Alpaca, single turn, using simple plain text delimiters. The next generation, things like the shared GPT format used by Vicuna, introduced explicit role labels like user and assistant to make multi-turn chat possible. And that brings us to the modern standard, like OpenAI's ChatML, which uses special reserved tokens that the user never even sees. This approach gives you way more security, which is absolutely essential when you start building complex agents that need to use tools.
So, after all that analysis, what's our final assessment? What's the engineering verdict on this pivotal historical artifact?
Okay, here are the key takeaways from the lab today. First, Alpaca was an absolute catalyst. It proved that low-cost, open-source instruction tuning was possible. Second, its simple, structured format basically became the blueprint for modern prompt engineering. And those core principles, like using explicit signals to separate tasks and define roles, they are still fundamental today. But, and this is the big but, as we move toward more sophisticated, multi-turn, agentic systems, it's crystal clear that we need more robust and secure formats that build on that incredible foundation.
And that leaves us with one final important question for you and your own work. The next time you're designing a system, take a hard look at the prompt formats you're using. Ask yourself, is this just a historical artifact, or is it a modern, mission-critical tool? Are you building on the foundations of the past, or are you truly engineering for the future of AI? That's all for today's session from the lab.